All right, then it's okay. Why don't you just stop it now, then? All right, we'll just, is that, let's just say just a minute. I want to see if our microphones are working all right. There they are. You check yours. Good. All right. Fine. We're all set. All right. Then and the focus is okay as far as you're concerned now. All right. Well, then, as I say, I'll just say a few words for identification, and then I'll say, please proceed, Mr. Rupp, and then you start in with saying something about the origin, just like we said,
radioisotopes, so forth.
That's right. And then we'll just take it from there. And then when you want to stop for a rest or something, hold up your hand like that, okay. And she'll stop it, and there will be no glitch whatsoever. All right. Well, fine. For identification, this is an interview with Mr. Art Rupp, and the date is February 1st, 1989. And with this, Art, will you please proceed?
Well, Clarence, we were talking a while ago about the origins of the radioisotope program, and I expect that the point I should make at first is that radioisotope interest didn't start with the Manhattan Project and reached clear back into the 30s when Irene Curie first made phosphorus 32 using alpha particles. So I always look at that as the beginning of the radioisotope manufacture, although at the time they didn't really realize what they were getting into. Then in the period between the early 30s and the time the Manhattan Project came along, there was a tremendous amount of work being done in the universities all over the world. And cyclotrons in California, and Cockcroft-Walton machines, England, and various places making isotopes, radioactive materials that could be used in chemical work tracing primarily. So at the time of the Manhattan Project, the people who were doing chemical work, chemical separations work primarily for the plutonium process, needed radioactive isotopes of one kind or another to assist in their work. So this was, in addition to the fission products, some of the simpler isotopes such as sodium-24 and a few others like that they wanted to use in chemistry were used here at the lab at Clinton Laboratories, and it so happens that when the graphite reactor started, one of the first parts of the program was to encase pure chemical target material in aluminum tubes, seal it with a sealer much like one of the can sealers, and put them in holes in a graphite stringer, we call it, a rod of pure graphite. This was stuck into the side of the pile and radiated anywhere from a matter of hours up to sometimes we radiated some material for months, depending on the half-life of the material that we wanted to make. Well, these were then taken out and put into shipping containers, which were essentially lead pots with good closures, and these were put into heavy wooden boxes and could be sent out to various chemists all around the university group, primarily, who wanted to use them. So that's probably the origin of the first radioactivity that was sent out from the laboratory, if you discount the bits of solutions that scientists had around the lab and they traded with people at universities all around the country.
This was before any real organized plan to extend broadly the uses of radioisotope, I take it.
That's correct. That didn't come along until shortly after the close of the World War II. And a group of people at Clinton Lab, Waldo Cohn and others, wrote an article for Science magazine, which in effect was partially a catalog of materials that one could get at the laboratory.
Yes, this was, in other words, late in 1945 then, probably.
I would be late in 1945, yes.
Yeah.
It actually started probably a little before the war ended, because the people who were involved in could see what was coming, and there were demands for isotopes, so it sort of slid right through the end of the war there, and they were ready to go.
Fine. Well, that was very, very interesting the way this originated, and apparently the demand was almost automatic for many of these.
The demand was quite great, and came from universities, as I said, primarily, but then all sorts of institutions, and then the sister laboratories around the country also wanted radioactivity. So it picked up quite rapidly. For a long while, the only isotopes that we shipped out to speak of, as far as variety is concerned, are those that were irradiated directly in the pile. And that included not only chemicals, but it included a great assortment of things, from, as I recall, piston rings to teeth to grain to insects. All sorts of things were irradiated in the pile and used either at this laboratory or at others. The next phase of the radioisotope program was one that of separation of isotopes in more or less pure form. And one remembers that the three that were the most important, and still are quite important, and I should mention, I guess, carbon-14, the most important of all the isotopes in some ways, and phosphorus-32 were two of those that were worked on to be separated from large amounts of target material, and after isolation, worked down into a small solution and suitably packaged and sent out.
Can you give us an example of how you would prepare, for instance, phosphorus, what the target material was, and what the nuclear reaction was?
In the case of the making phosphorus-32, the radiation target was sulfur. So it required quite a large amount of sulfur for a target to make a reasonable amount of P32, because the graphite reactor didn't have as many neutrons of the right energy, because it is a so-called NP reaction, which requires something other than the slow neutrons, which of course operate the reactor.
In other words, the slow neutrons didn't have the energy necessary, and so you used only the high energy spectrum of the pile.
Right. Of course, we made no special effort for screening there. It's just the yield resulted from whatever we got.
Oh, yes.
So after that, the sulfur, incidentally, was melted into a big aluminum can about so big, like this, which is a big target, and had a sort of a built-in funnel top, and it was melted in there, closed up, and then lowered down into the pile, radiated probably, as I recall, a week or so, because phosphorus-32 has a half-life of only 14 days anyhow, so usually if you irradiate 1 or 2 half-lives, it's quite enough. Well, then it was taken out, and we first separated phosphorus from sulfur by what we called the strong arm method, so to speak. It was really what it amounted to was melting the sulfur again in a big beaker, and of course this was done by some rude remote control apparatus. And then we had a vat of nitric acid, not concentrated nitric acid, but quite strong, I call it concentration. And it was poured down through the solution, dribbled down through it, and an extraction took place into the nitric acid.
Oh, yes.
So, and then the nitric acid was drawn off later, and by various carrying methods, usually an iron hydroxide or lanthanum hydroxide, we would pull the phosphate out and then pass it through several other chemical procedures to get the phosphorus free, as usually being sent out as very dilute phosphoric acid.
Oh, yes. Fine. And how about there was some sort of a equivalent reaction in making carbon then?
Now, carbon is an interesting case because right from the very beginning, one of the most sophisticated possible methods was used for making carbon-14, although it wasn't very practical at the time. And this is a loop in a reactor containing, the loop contained ammonium nitrate.
Oh, yeah.
And the nitrate is the target atom, the nitrogen-14, to make the carbon-14.
Oh, yes.
Can have an NP reaction involved. So Art Snell and another group in physics put together an apparatus where we had a loop that would go into the side of the reactor and into the neutron zone and back out again. And it came out to an apparatus where we could aerate it. Well, actually, we were using nitrogen, or at that time, and would aerate the solution at somewhat elevated temperature. And the bit of carbon that was in there usually appeared as carbon dioxide. Some of it would appear as methane, and a tiny bit, as I recall, would appear as carbon monoxide. But these would be swept out of the stream and captured in a column, for example, and then taken out by flushing the columns and working it up finally as barium carbonate.
Oh, yes.
Now, barium carbonate was the way it was shipped. The interesting thing about that method, compared to the later ones we used, was that the specific activity was very high. And this was because of the separation practically at the time that it was made. And if the substances were pure and there was very little carbon in there, then it was contaminated with very little of it. So we got preparations of carbon-14 where over 50% of the atoms were carbon-14 atoms.
That's astonishing.
It was extraordinarily good.
Yeah.
Later on, we used calcium nitrate for targets for mass production. And the specific activity in that case would run, certainly not over 10%, and usually around 5%. But this was quite adequate for the work that was being done at that time, and they wanted to make organic compounds labeled with carbon-14, so they would have added carrier anyhow.
Oh, yes.
The very high specific activity, carbon-14, was mostly of interest to the physicists at that time.
When was the first shipment of carbon-14 made to, you might say, to outside the project?
Well, the first shipment, I don't remember where it was made to. It was made to the Bernard Free Clinic in St. Louis.
Oh, yes.
And it must have been about 1945.
Oh, yeah, right, very early.
Very early, yeah, 45, 46, yes. And so that the use of carbon-14 is something that grew very steadily all through the years of the radioisotope program.
Oh, yes. As a matter of fact, interviewed Martin Kamen, who discovered the reaction, and
he was at St. Louis.
I asked him, how many research papers used carbon-14 as part of it, and he said, I have no idea, but he says it's probably between 50 and 100,000 papers.
At least.
He said almost all of the work that's done has been done by virtue of using carbon-14.
Well, of course, it's easy to see how important it would be, since the entire system of chemistry is based on carbon, so naturally it's tremendously useful.
Yeah.
And actually, a lot of the 5,000-year half-life that it had is not too bad. Some people at times said that wish it had been created with a half-life of a few hundred years, but so that we get more activity for measurement. But the 5,000 years seem to have worked pretty well on it.
Yes, it's an interesting thing. Dr. Kamen mentioned that as far as the half-life, I believe there is some carbon isotope that has a much shorter half-life with a cyclotron produced in, and so they wanted to get another one. They said, we'll try carbon-14, and Oppenheimer said, yes, but that'll have only a half-life of a few seconds from theory, and so sometimes the theory doesn't work out.
Yeah, well, it turned out to be really a pretty suitable half-life for many things. The other important isotope, Clarence, was iodine-131.
Oh, yes.
And I put a great deal of effort into that because it turned out to be a very useful isotope, not only for following thyroid studies in medicine, but for tagging things in general.
Oh, yes.
Iodine can be hooked on to compounds having double bonds with the greatest of ease, and it was used in everything for tracing oil in pipelines to very sophisticated compounds in medicine they wanted to tag.
Oh, yeah.
So we worked first by making it from tellurium, radiating tellurium in the pile, getting a transmutation, and then dissolving the tellurium in sulfuric acid and a catalyst, selenium catalyst probably, I recall, distilling the iodine off, and it's quite volatile, comes off with the steam, and then refining through a number of distillations to get it to high purity. And in the final shipment, a very tiny amount of hydroxide was added to stabilize it for shipment.
Oh, yes.
So a great deal of iodine-131 was used through the years, and was the first one where I decided that we would have to try to get it from fission products.
Oh,
where we could get a vast quantity of iodine. So it was the incentive that we had for our first work on fission product materials, and we used slugs out of the graphite pile.
Oh, yeah.
And we had a tantalum-lined dissolver down in the old C building.
Oh, yes.
And where we dissolved it in nitric acid and distilled the iodine off, and of course we bled off the xenon and krypton to the atmosphere in those days. And
yes. Incidentally, if I could interrupt just a second, what actually do you remember the approximate date that you yourself started into the radioisotope program?
1946, probably.
Well, right at the start,
somewhere
after
toward the end of the year.
Yes.
Because I was working over in another group with Miles Levert.
Oh, yes.
And working on development, and then it was decided to form radioisotope into semi-business type operation under Logan Emlet.
Oh, yes.
So I transferred over and worked for him in operations division, and we started developing these processes for making all the isotopes and getting them all cataloged and sent out to all people who might want them. And through the years, we also tried to increase the variety and chemical form that we could send them out in. So the fission products, which was always have been of great interest to me, and I certainly remember your great interest in helping us along with the fission product project to get large amounts of fission products. And that did go through. We finally got around to the point with the fission product plant where we not only could, but we did separate literally millions of curies in pure form. As I recall, the largest amount that we made in pure form was cerium-144, and this was several million curies of pure cerium as the oxide. This was the type of thing that you had to use water-cooled tables to keep it on, water-cooled tongs to pick it up. It would just, of course, glow tremendously in the dark.
Oh, yes.
And all of those problems we solved, which in retrospect, I think they were rather tough problems, and we solved them fairly easy as we went along.
That's amazing, because you had to work by remote control all the time.
Right.
And the chemistry is not all that simple on some of these things, and so you were able to produce these very, very intense sources. Incidentally, what was the requirement at that time for these for the cerium, as an example?
Well, cerium was one that we really didn't make very much of, but we happened to have an Air Force special contract at the time.
Oh, yes.
And they were interested in the possibility of using cerium to heat hydrogen for a rear thrust from a rocket.
Oh, yeah.
And that would give you a maximum thrust.
Oh, yes.
Using hydrogen gas heated by cerium. That particular one project, of course, never did get to any really big scale, but it was always been interested in it.
Yes, it's a very, very interesting,
it was an interesting
experiment.
And I remember at the time, you possibly have forgotten, you were very interested in that. The cesium, we were interested in getting a 30-year gamma emitter that would do the work that cobalt-60 does. And it was always offensive to me to have to put material into the reactor to make more radioactivity when we had so much radioactivity already we didn't know what to do with it.
Oh, yeah.
So it seemed to me that it was only a matter of good sense to try to use cesium-137.
Which has such a big yield.
We've got so much
reactor.
of it, yes, the big yield. And we made those in form of cesium chloride and cesium fluoride, and we were able to make the pellets using a hydraulic press on the inside of the cells, of course, and getting little blocks of cesium chloride about so big around, it was thick. They sealed these in double capsules of stainless steel, and they were used in therapy machines, most particularly at Oral.
Oh, yes.
And they're still being used to some extent, much smaller ones for radiography of all kinds. But the other one that we were interested in was strontium-90, which is that horror isotope. And we made literally not quite 1 million curies of that as the oxide, and pressed it out in wafers and used it for heat sources. And we have one source at the laboratory, which was originally used in Antarctica for generating power for a beacon.
Oh, yeah.
I think it's still delivering quite a respectable amount of power. It's by thermocouples fitted around the source.
What's the half-life of
well, it's about 30 years, but it's even in that late date, there had been some controversy about whether it was nearer 29 than 30.
Oh, yeah.
And I haven't really read on the subject in a good many years.
Oh, yes. Mm-hmm.
For all practical purposes,
for all practical
30
purposes.
years. I always thought of cesium and strontium's 30-year activity.
So the heat source would have a long life.
Have a long
for
life.
Practical applications.
The ones that we've made, and I was interested one time looking at that one, is half gone now. Oh, yeah. And this is people who talk about radioactive waste never think of. This is a waste that disappears by itself if you just wait long enough.
That's right.
I calculated one time that if we had a plant connected with a reactor and it was making the products, the usual fission products, and we separated them in a fission product plant and canned them up and put them away, that after about 75 years, it would be at equilibrium. Oh, yeah. The plant would be, the strontium and cesium, the particular items of interest, would be decaying about as fast as the reactor is making them.
Oh, yeah. So the world would not increase its radioactivity.
I regret that this point is never brought out in articles or discussions on these. They talk about bacteriological waste, and now that's going to increase by leaps and bounds. And many wastes are at least stable material, lead, mercury, cadmium, and so on, they at least stay the same. Radioactivity disappears by itself if you're patient enough. So we were hopeful that there would be more interest in concentrating fission products, using them where you could, storing them where you can't otherwise, and just taking care of them, in other words. So that this was one interest of mine that I tried to pursue, but I don't think anything ever came of it from the standpoint of making highly concentrated, separated materials.
Yes, I know you had written several articles on removing some of the fission products and essentially canning those, and then I believe there were some others in a little different category, and this would be a wonderful way to manage the waste.
Wonderful way to manage the waste. That is exactly right. It is a very good way to put it. Yeah. When talking about reactor waste, it's customary to group radioactivity all together as if it were equally dangerous. And that, by a large measure, is not so. Strontium-90, of course, being far more dangerous than the rest of the material. If one just took the strontium-90 out of it, you would practically pull its teeth, because the plutonium, of course, would already have been taken out, and the others will decay in a very respectable amount of time. So the consideration of taking out material was always run down by people who did not like those processes by the fact that you couldn't achieve essentially 100% decontamination. And it would take a long time to go into explanation, but that's essentially a phony argument. Oh, yes. This, of course, our society is cursed with this 100% safe, not only in radioactivity, but in almost every other form. Right. A new drug has to be 100% safe, and so people are dying because of the unavailability and all the way through the rest of things. But that's neither here nor there. But the radioisotopes have continued to be such remarkable use throughout the years, and the benefits are incalculable. Mention one of the stories, having been talking about iodine, that is illustrative of several things. Dr. Yallow, who's did most of the work on radiometric measurements of the enzymes in the body and so on. And we talked together years ago about iodine, and iodine now has an 8-day activity, and this means that 1 curie of the material has a relatively few atoms. I don't remember now, a few million, not very many. But for the purposes that she had in mind, which is typical of a lot of biochemical work, she wanted to tag the material, and then you dilute quite a lot as you go through. And if you don't have enough of the atoms of the tag on there, iodine, radioactive atoms, you come around to a final sample that you can't measure because of the statistical counting that you have to have in any kind of a counting apparatus.
Oh, yeah.
So it was very important to achieve a high specific activity, which we did by very special handling of target material in the reactor. This case, a small amount of uranium-235 in an aluminum matrix. We irradiated that, and we were able to get a sample of iodine that was, as I recall, around 80 to 90% of atoms in there were radioactive atoms.
Oh, remarkable.
Which is allowed then a tagging of such things as enzymes, hormones, so that one could still make radiometric measurements.
Yeah, so she got her the Nobel Prize, I believe, for this work that she did. That was a very brilliant application there.
We did a similar thing there on that in assist on the development of the maser with Town at Columbia, I believe, where we had to make a sample of chlorine 36, which is a 100 or 200,000 year half-life. At a very pure material, and we attempted to do this in somewhat the same way. So there were special problems of these kinds that came up all through the radioisotope program, and I think one of the things that we did do and tried to do is to get every special requirement of the scientific community taken care of as well as we could. That's one of the things I'm most proud of.
Yes. Well, of course, every physicist I've talked about pays high tribute to the isotope program, because without it, it would not be possible to do that work.
We understood very well the work that was going on, and we were highly pleased to be a part of it. I guess that's
right. Go.
The applications of material to some of the project work is also important. One particularly important isotope, which carried the code name Rala, was actually barium with the lanthanum daughter, barium-140. That was sent to Los Alamos, where by utilizing the intense gamma rays from the hundreds of thousands of curies of lanthanum that was separated from it, they could analyze the shock waves and do other important work there related to the design of the bomb. A similar material was made by us of point sources of strontium-90, which would shoot out beta particles, high-speed electrons that were fixed into rotating wheels that would send pulses through the explosion waves for analysis, for example. Those are just two examples of many, many of the things that physicists did. There's just no end of them, that where one could use either a gamma ray for measurement or a beta particle for measurement on the actual explosives that they were working on.
Incidentally, what was the half-life of the barium and the lanthanum?
It was only around 12 days for the barium.
For the barium.
The lanthanum daughter was equilibrium with that, but I don't recall the half-life. It was very short. It was just an equilibrium daughter.
Yeah, an equilibrium daughter.
That they used. Many of the other isotope uses were in the field of agriculture and, of course, medicine. In agriculture, there was a very intense period of research in the early years of the radioisotope program, where the United States Department of Agriculture and others determined the ways in which phosphorus and nitrogen and carbon and potassium were used in plants. And that seemed to me like a period of about 4 or 5 years, a very high peak of research activity when they discovered most all the essential things about the movement of atoms in the growing plant. And a lot of that work was done at Beltsville, Maryland, at the farm station there.
I imagine that phosphorus was certainly used tremendously in this.
Yes, phosphorus was very interesting, and it was used also by lecturers by taking leaves and at the beginning of a lecture putting a stem in a solution of phosphoric acid, and then after a while take it out and either photographed it against a fluorescent screen, and you could see all the little veins all through the thing where the phosphorus had been taken up into the leaf.
Oh, yes.
It was a favorite demonstration. This sort of work was done on a great many plants, and as I say, it was just a fierce amount of research that was done there over a period of 4 or 5, maybe 10 years, I recall now. And they discovered just about everything that they needed to know, at least at that time. So, then the industrial use was considerably slower. One of the reasons there, I suppose, was the nature of industry as compared to biological sciences and medicine and so on, not nearly so adventurous. And there, even in that early day, radioactivity had a bit of a danger tag on it, so it was slower there. But one of the first uses I remember is the radiation in the pile directly, piston rings, gear parts, sleeves, all the parts where wear occurs. And they were running tests on engines, and the oil monitored continuously, and the wear on the sleeves under different conditions monitored after taking them out. There was a lot of that kind of work which had to do with the wear of mechanical parts, and much of that, as I say, was done fairly early in the program. The pipeline usage was another that developed early. When oil is shipped through pipelines, it has all different kinds of oil in the pipeline. It's not one single kind. They'll send through a batch of gasoline and kerosene and crude oil and diesel fuel and so forth, and they're usually separated by water slugs in between them. And there was an early usage there of tagging the water plugs, and they had equipment, then you could tell about where everything was in the pipeline and when it was coming through a station. You could make your necessary switch over it. Then in refineries themselves, on moving catalysts was another, where they needed to find out how the catalyst was being worn down, what the movement was, what the turnover in the bed was, and these could all be measured by sophisticated instrumentation that they might have had at that time, and much more so now, of course, of how the cracking process was going along. Any sort of a manufacturing process where there was a need to know where a particular component was at a particular time and where it was passing, one could do this. And tank level is another use that has hung on pretty well. Usually cesium sources are used for this. If you put a source on one side of a tank and a detector on the other, by suitably measuring the gamma rays that pass through the tank that are attenuated by the liquid moving up in the tank, and the source is here, and the detector over here. It'll go through varying amounts of liquid, and you can tell what pretty accurately, even down to the number of pounds in the tank. So there are a lot of uses like that that are very practical. Then another thing in the pipeline industry was the radiography on the spot of welds that were made, and for this iridium was used. And I regret I don't remember the number of the isotope now anymore, but it's a very useful gamma emitter for. It could also be pulled through the pipe, so it could be X-rayed from the inside out, and that was very handy. It still is. So there are innumerable uses similar to that in the industry, but it didn't grow to a point as far as I think it could have because of some of the fears of radioactivity. And the most notable on that is the use of radioisotope large sources for sterilization of materials. Most of the bandages and needles and so forth that are used now in operating rooms around the country are sterilized by radiation.
What radioisotope is sources?
They primarily use cobalt-60, but some of them are equipped with cesium-137. But the use for food has never been able to get over the hump very well, primarily sponsored by the Army at Natick in Massachusetts. And it was a very good program. It worked quite well. The motivating force there was to have field rations for soldiers that were essentially fresh.
Oh, yes.
And I remember tasting some of the bacon and biscuits and so forth that had been radiated. And it was so months and months after it had been made, it was quite okay. But, for a very simple process for eradicating larvae in grain and in spices and things of that kind, they all worked quite well, but it has never been applied in the fashion that it could, and I'm not exactly sure why. There's a lot of grain spoilage around the world, and it's certainly something that could help with it, because a lot of grain is just wasted by spoilage. And the radiation of grain in silos has been tried, and it's probably practical if they really worked on it. But that's another usage that is lying there dormant, still to be worked on. We were talking there. What were one of the other suggestions there that you were thinking about a moment ago?
Well, let's see. We're talking about. Well, let's see. We've already gone through the agriculture and the
most of the fields of science,
and actually most of the fields of science you use it more or less continuously, and medicine, of course, continues tremendous use of radioisotopes. So it certainly is a big thing with regard to specific isotopes. I guess at some time or other you've gone almost all the way through the periodic table for highly specialized scientific uses and targets.
For help with scientific programs, we have made just about any isotope that is possible to make and to ship, and then made it very often in a form that they needed it in most cases. But they should mention here, when we were talking about medicine, that probably one of the most important uses today is in radiometric procedures. In other words, I think you could hardly find procedures in hospitals anymore that are not done by radiometric method. In other words, by tagging special compounds that are counted are either discarded in the subtraction made to get the radiometric measurement. It's a very important thing, and this is literally done in, I know, hundreds of thousands per day across the country, and perhaps millions, for all I know, of for laboratory procedures that is done every day. These are small companies, of course, of well, some of them are not so small, that have grown up to make specialized forms of isotopes that can be used for all these radiometric measurements for everything from thyroid, one of the simple things like that, to measuring the hormones in the body. Many of these procedures that could not be accomplished without using a radiometric procedure.
Oh, yes.
This probably, of course, a lot of people don't realize the importance of the radiometric procedure.
In fact, they may not even know it's being used.
They quite likely don't know it's being used.
Yes. Well, that's this is it's fascinating, the number of different applications. And as you mentioned something about how some of these applications have gone on broadly, and there are many companies in the United States that use radioisotopes for medicine medicine preparations and so forth, and actually, I guess in many of these things, the laboratory pioneered in developing methods for preparation of radioisotopes, and then passed them on to an industrial process, which created many businesses throughout the whole United States. Would you like to say a little bit about some of the way some of the businesses developed from the pioneering work which you did?
There were quite a lot of them that did develop. One of the earliest that I remember was Tracer Lab.
Oh, yes.
In Boston. And these companies were able to do a lot more service work, of course, than we were at the laboratory. They were able to personalize the service, and those radioisotope forms that were popular, it could make a lot of them. And so there were a number of companies that specialized in carbon-14 compounds. So while we originally made a few of the carbon-14 compounds, it wasn't very long before this was a private industry enterprise, and there were perhaps dozens of companies or more that were specialized in making carbon-14, and then later those that are also tagged with hydrogen, tritium, and the tritium is one of the most used isotopes today, 12-year activity, tritium. There are many fairly large service companies. One that I did consulting work with after I retired, the Mallinckrodt Corporation, made material in fairly large quantities and shipped it to other smaller outfits who finally turned it out in dose form. So there has not only been one type of company, but a number of types of companies that have spun off from this, or making radioisotopes available in usable form.
Oh, yes.
Now, some of the most usable forms, and it sounds like the wheel turning back again, come from very short-lived isotopes made from cyclotrons now.
Oh, yes.
And there's a new generation of cyclotrons where they make short-lived iodines. And these are favored now because lowering the dose of radioactivity that the patient might receive is quite good. So, for example, Mallinckrodt does have their own cyclotron.
Oh, yes.
So that fewer isotopes are made in reactor and more in the cyclotrons.
Oh, yes.
I think this is a trend that probably will go ahead slowly. I think there'll be more in specially designed cyclotrons for making various kinds of radioisotopes.
Oh, yes.
one of the things along this line that you're very familiar with is that I was interested in isotopes that by no matter how one figured it, one could never get them in extremely high specific activity. So we took a page out of the stable isotope method, where the calutron, which is a magnetic separation of the atoms by their different mass, wanted to eventually get some specially designed calutrons that could separate some of the highly radioactive materials, primarily at that time for scientific purposes. But that never did quite gel. But it is quite possible, it's feasible. And we did it with plutonium quite easily. And using the radioactivity in the calutron, which is used for stable isotope production, we could get high specific activity materials that could not be gotten in any other way. Because there was no isotope flux that would be high enough to get all of the atoms converted. And there's only one case that I can think of where we utilize a similar method, or not similar, parallel method, of burnout of material. We took targets of cobalt to irradiate them, and we literally irradiated them until we burned all of the atoms of cobalt-59 in there, converted them either into cobalt-60 or into the decay product, nickel-60. And then processed the cobalt afterwards, taking the nickel out. And what we had was a preparation with all of the atoms, essentially cobalt-60 atoms. So that is another method of achieving extremely high purity or high specific activity. These are typical of problems that we like to work on, but there's not necessarily the industrial or even scientific incentive in a lot of cases. It's just things that one would like to do to see if we could do it.
Essentially stretch the boundaries of science.
Stretch the boundaries of it. But we did make a lot of materials that were essentially pure. And once I remember making a sample of cesium-137 that was extremely pure. Then we allowed it to decay for, I think it was 7 or 8 years. Then we separated the barium, stable barium product from it, and determined the true half-life of cesium by measuring by weight on the balance. The barium that had been.
It's all right.
The barium that had been produced. I always loved that little experiment.
But that's fascinating. So you really got a real measurement.
That was a real genuine measurement with using genuine atoms that we measured on a balance.
Yes, that's it. Now let's see. I know also, of course, in connection with the Oak Ridge Institute of Nuclear Studies, they had a program for training people for use. For using radioisotopes, and then they would go back to various parts of the United States and then order radioisotopes. And also, I was wondering if you had anything to say about your orders from on the international front. There must have been a lot of aid that you gave on the international science front.
There are quite a number of years that we were the sole supplier of radioactivity for the entire world. Essentially, there was, except for a cyclotron here and there, but any fairly large amounts we supplied. And we worked with the people in England in establishing their at their radiochemical center, which was formerly a place for separating radium compounds.
Oh, yes.
And that started the English program. And we did a great deal to start that in the design of the equipment and the buildings and the site. And then furnished materials to essentially all of the countries in Europe, and a good bit of the rest of the world where there was a scientific interest.
So you made available then the science and the technology to enable these people to produce it in their own countries. Then.
Yes, there were several ramifications of that where eventually a technique of producing radioisotopes where one could essentially milk off of an ion exchange column came to be a technique that was used a lot. And this is a case where the mother radioisotope has a fairly long half-life and the daughter has a short half-life. And you could use this by passing a special solution, eluting material through the column and draw the daughter off in pure form, sometimes even as short as a few seconds. If you could had an experiment that you could run that way. And that's another way that they're able to ship materials around the world. One of the most used right now is the molybdenum column. They called, Marshall Brewster liked to call them cows.
Oh, yeah.
Although I didn't particularly like that term. But I called them generators. The technetium-99M, which is used for scanning primarily, is one of the most used today. A lot of that work was done by the people at Brookhaven National Laboratory.
Oh, yes.
And each one of the labs, of course, did pick out, as you know, certain projects that they specialized in.
Oh, yeah.
And the generators were developed to a great extent by the group there at Brookhaven. We all did make them and ship them, and there are new ones that have been made also that one can use. Another thing that we developed was the use of stable isotope targets.
Oh, yeah.
In order to get highly concentrated and highly pure material, because there were no side reactions. If the atom that one wanted to bombard with neutrons was a nearly pure atom of your target material.
Without complicating isotopes.
Without complicating isotopes. So we introduced the use of stable isotope targets. We were by that time all part of the same group, and we worked together on it.
Oh, yes.
And made all kinds of targets, and in addition to that, made them into forms that were sent out in the form of cyclotron targets, which are very often copper plates with material plated on in various ways for use in cyclotrons. So there are a lot of services like that that were developed through the years. Many of those things, of course, have been taken over now by private groups around the country, and policy of the government on that was to always, if it was shown that service could be given, the material produced by outside outfits, then generally speaking, we withdrew from the production.
And well, incidentally, however, I'm sort of lost contact with this. But are there? How big is the program in Oak Ridge now? In other words, it's.
I'm not too familiar with the details now, but it's primarily down to irradiating large amounts of material. For example, cobalt for cobalt-60.
Oh, yes.
Special, very useful new isotopes for heart studies. I've forgotten now what that is. There are specialized materials in general that either can't be made by other places, or the interest or the commercial and economic interest is high enough for outside groups to do. But I think they do several $1 million worth of visits a year yet.
Oh, yes. And mostly for these specialized applications.
Yes, either very large amounts of something like cobalt or something that's not made very easily at other places.
Well, this is certainly a fascinating exposition of the origin and course of the use and applications of radioisotopes. Before closing, though, I wanted to see, are there any other miscellaneous remarks in this program that you may have forgotten?
Well, over a period of time, we realized that we were in a group that, as far as production was concerned, we were going to work ourselves out of business, so to speak. And this was never to be an enterprise that was growing in actual size, particularly as measured by dollar input. So there were facets of it that were developed and financed by the government that were along the lines of information collection and putting out a magazine, which we did for a number of years, of Science of Technology magazine, in which we reviewed all the current work that was being done. And these are still around in libraries and archives of the work that was being done. I think that in the latter years, it was important to get out information on what had been done. And this is one of the things that we tried to do.
Oh, yes. Well, fine. In other words, essentially, you established the business, established the technology, got the technology out into widely separated parts of the United States and the commercial world, and it's going on full force in the United States and the world in general. So essentially, you accomplished your mission, and the world.
I feel very lucky.
Yeah, the world is still benefiting from all of those activities.
I hope that will still develop. One never knows where an interesting item is going to crop up in research.
Fine. Well, thank you very much, Mr. Rupp, for this very illuminating discussion, and I'm sure that this tape may be of interest to many people who are interested in knowing about the history of the field.
Thank you very much.